Hola chicos. Voy a esperar 2 minutos. Pues empezaré. Um, Voy a tomar una otra clase de español. Ahora estoy tomando una clase de español 1 y, cuando nosotros regresamos en la escuela, uh, voy a asistir a una clase de español 3 también. Por lo tanto, tendré 2 clases de español. Okay, good morning. I think I'm going to start now. I hope everyone's doing well. Okay. So this is AP Physics 1, 319, and this is period 6. Okay, so this is going to be our last waves lesson, and we are going to talk about the Doppler effect, sometimes called the Doppler shift. Okay. So before I say what the Doppler effect is, I just want to describe the scenario in which you encounter the Doppler effect. Okay. So you have a source of a wave. Okay. And so the source is emitting waves. And maybe the source is emitting waves of frequency 1,000 hertz. Okay. Now the source is going to be moving. You know, it's moving. It could be moving left or right. It doesn't matter. Or up or down in any direction. And so I'm going to call V sub S the source speed. Then we have an observer of the wave. So we have a thing that's creating the wave and a thing that's perceiving the wave. And so the observer is also moving. And we are going to call V sub O the observer speed. All right. and so what we will find, and I'll call f sub o the observed frequency, and the observed frequency, even though the source is emitting 1,000 hertz, the observed frequency that the observer measures will not be 1,000 hertz. Okay? And so that is what the Doppler effect is. Okay? It is a shift in the measured frequency when the source of a wave and the observer of a wave are in relative motion. Okay? So the emitted frequency is not going to be the same thing as the observed frequency when they are, when they're in relative motion. So let's try to understand why the Doppler effect happens. All right. So if we think about our fundamentally wave equation, which is v equals lambda f, speed equals wavelength times frequency, and we rearrange that equation, we can see that the observed frequency is going to be equal to the measured wave speed divided by the measured wavelength. Okay, so that's just taking both sides and dividing by wavelength. Okay, so let's think about what happens. So if the observer is moving, this will change the measured speed of the wave. So, for example, let's, and we're going to be talking pretty much exclusively about sound today. So you have a sound wave that's going, at 340 meters per second this way. All right. What if the observer of this sound wave is moving this way at 330 meters per second? All right. So basically, the observer is trying to run away from the wave, and they are almost succeeding. Because of this relative, the motion of the observer, this person is running away from the wave. So from the perspective of the observer, the wave is traveling, or I should say approaching, at only 10 meters per second in this case, right? Because as 1 second passes, the observer moves forward 330 meters, the wave moves forward 340 meters, so it got 10 meters closer in that 1 second, okay? So see how the observer moving affects the speed that the observer sees the wave traveling at, okay? So the measured speed of the wave changes when the observer moves, okay? And then also, if the source of a wave is moving, this will change the wavelength. Okay, so let's see how that works. Let's suppose I have a source of a wave, and the source is not moving. Okay, if the source is not moving, then if we were to look at the wave fronts, so look at the waves that are being emitted, they are basically a bunch of concentric circles. Like that, okay? So what are we looking at here? We're kind of like looking at the wave from above. These are crests of the wave that are traveling outwards, okay? And so if you wanted to know what the wavelength is, you would measure the distance between crests. So that distance right there is the wavelength, okay? So this is when the source is not moving. It's just you have all these concentric circles, which are the wave radiating outward. But what if the source is now moving? So let's imagine that the source is moving in this direction. All right. Then on the leading side of the source, the waves are going to be scrunched together. So I'll try and draw this as best I can. Okay, so it kind of looks like that. And so what you can see is on the leading side of the waves are scrunched together, and so the wavelength is smaller on the front side. And on the trailing edge, on the trailing side of the source, this would be the wavelength. And so we can see that on the front side, the wavelength is smaller, and on the back side, the wavelength is longer than what we had in the case where the source is not moving at all. Okay, so the measured wavelength changes when the source moves. Okay. And so here's the rule for figuring out how the frequency is going to change. All right. So if the source and the observer are getting closer as time goes on, then what we will measure is that the observed frequency is greater than the emitted frequency. Okay? If the source and the observer are getting further apart, then the observed frequency is going to be less than the emitted frequency. All right. So let's just do a couple examples qualitatively to see how that works. All right. So what if we have the source here and the observer is here? Oops. And what if the observer is moving to the right at 50 meters per second? And then the source is also moving to the right at also 50 meters per second. Okay, so in this case, the source and the observer are both moving, but they're moving at the same speed, and so they're not getting any closer together and they're not getting any farther apart. And so in this case, the observed frequency is going to be equal to the emitted frequency. Okay. What if we have a situation where here's the source, here's the observer, and let's say the source is moving to the left at 50 meters per second, but the observer is moving to the left at 100 meters per second. So it's like a chase is going on. The observer is chasing the source. And because the observer is going faster than the source, they're going to be getting closer together as time goes on. So the observed frequency is going to be greater than the emitted frequency. All right. What if we have a situation where the source is at rest? Okay. And the observer is traveling to the right at 50 meters per second. So in this case, because the source is at rest, the observer is going to be getting further away from the source. And so for that reason, the observed frequency would be less than the emitted frequency. Okay? So that's qualitatively how it works. And that's very important when understanding the Doppler effect. You should be able to predict, is the frequency going to shift up or down compared to the emitted frequency? All right? So there's an equation that I will teach you at this time for how to calculate the observed frequency. All right? So the observed frequency is the emitted frequency times a factor. And that factor is V plus or minus VO over V plus or minus Vs. So notice how the observer appears on the numerator and the source appears on the denominator. That is because of this equation right here, where I said that the observer changes the speed, which is in the numerator, and the source changes the wavelength, which is in the denominator. So that's why, I'm not going to derive why this equation is true, but that's why the source appears in the denominator and the observer appears in the numerator. Okay. So what are these? Well, VO is the speed of the source. Vs is the speed of, mix that up. I'm sorry about that. VO is the speed of the observer. Vs is the speed of the source. And V without any subscript is the speed of the wave. Now, because we are going to be dealing with 100% sound waves, this is going to be 340 meters per second under standard conditions. Now, notice how there's a plus or minus and there's a plus or minus. These pluses and minuses are independent of each other. So they could be both pluses, they could be both minuses. One could be plus and the other one could be a minus, okay? Depending on the situation, all right? And so which one you choose, you are going to use common sense. And so I will show you what I mean by that, all right? So, and it's important to have intuition, because the intuition is what gives you the common sense for what should happen, okay? One thing I want to note is that this equation does not work for electromagnetic waves. such as light or radio waves or X-rays. These are all examples of electromagnetic waves. Okay. Why doesn't it work? Because electromagnetic waves travel at the speed of light, and anytime something is traveling at or near the speed of light, Einstein's theory of relativity becomes important. Okay, and then that changes the physics. So this equation is derived without any knowledge of the theory of relativity, but it changes a little bit once we have relativity involved. All right, so we're going to do 2 examples, and then I'll do a little demo, and then we'll go to the Zoom room. So my first example, this is the classic example of the Doppler effect. We have an ambulance emits a siren of frequency 1000 hertz. The ambulance passes by a stationary observer at 40 meters per second. Okay, so we're going to analyze 2 cases here. So at first, here's the observer. At first, you have the source is going towards the observer at 40 meters per second. It looks like they're going to have a collision, but they just go right by the observer. And then after that, the source passes by the observer okay, like that. And then the source is going away. So at first, the source is approaching, and then after it passes by, the source is going away. And what we want to do is we want to figure out what is the observed frequency on approach, and what is the observed frequency after. All right. So when I'm doing Doppler effect problems, I like to plug in numbers and then determine the signs as the last step. Okay. So my equation is the observed frequency on approach is the emitted frequency, which is 1000 hertz, times, and then I have this fraction, and we have v and v, where that's both the speed of the wave, which is 340, the speed of the observer is at rest, and so therefore the speed of the observer is 0. And so for the numerator, it doesn't matter which sign I choose. Okay, so I'll just choose plus, because whether you add 0 or subtract 0, you get the same answer. The speed of the source is 40. All right. And then we're going to choose the sign in just a second. And then I have the exact same thing for after. All right. It's going to be 1000 times the fraction 340 plus 0 over 340 something 40. Okay. So let's analyze it on approach. Should it be a plus or a minus? Well, on approach, the source and the observer are getting closer together. So what that means is that this observed frequency should be greater than 1000, right? Because they're getting closer together. So the question is, which sign choice is going to make this greater than 1,000? Well, if I want to make a fraction bigger, I need to make the denominator smaller. Okay? So the way to make the denominator smaller wouldn't be to add 40, it would be to subtract 40. So the minus sign is the one that I will choose. All right? So this is going to be 1,000 times 340 over 300, which is 1,133 hertz. Okay? Now afterwards, the source and the observer are getting further apart. So the observed frequency should be shifted below 1,000 hertz. This is going to be below less than 1,000 hertz. And so if I have a fraction and I want to make it smaller, I need to make the denominator bigger. And so this will be a plus. And so I get 1,000 times 340 over 380, which is 894 hertz. Okay? So what would happen is, on approach, the frequency is shifted up. And then the moment the ambulance passes by, the frequency is going to shift down because it transitions from going towards you to going away from you. Okay? And so this is why you hear the classic Doppler effect sound. If there's an ambulance passing by, you hear meow, meow. Okay? The frequency is raised when it's approaching, and it drops once it's going away. And we just calculated by how much it will drop would be the difference between these two frequencies. All right? So that's nice. We'll do one more example. And this example has the source is emitting 1,000 hertz again, just because that's a nice round number. And the source is moving to the right at 100 meters per second. The observer is positioned to the right of the observer. Okay, and is going to the right at 200 meters per second. Okay. And so what we want to do is look at the motion of each separately. Okay? And that's how we determine whether it's going to be pluses or minuses. Okay? So if we look at ignoring the motion of the source, the observer is trying to move away from the source. Okay? So the observer is trying to lower the frequency. All right? And if we look at the source, ignoring the motion of the observer, the source is trying to approach the observer. So the source is trying to raise the frequency. All right? And so now what we do is we use our equation, we set it up. So the observed frequency is the emitted frequency times the fraction v plus or minus VO, v plus or minus Vs. So the emitted frequency is 1,000. V with no subscript is the speed of sound. VO is the speed of the observer, so that would be 200. Okay, Vs is the speed of the source, which is 100. Okay, so this in the numerator is the observer, and the 100 in the denominator is the source. Okay, so now to determine the signs, we have to look at what each motion is trying to do. Okay, so let's start with the observer. The observer is trying to lower the frequency. All right, and so we can see that the observer's speed is on the numerator. So if you want to lower the frequency and you're on the numerator, you're trying to make the numerator smaller, because a smaller numerator means a smaller number. Okay, so the observer's motion is going to make the numerator smaller, okay, because it's trying to lower the frequency. So for that reason, it's going to be a minus sign in the numerator. Okay. Now if I look at the source is trying to raise the frequency. The source appears in the denominator. So if you want to take a fraction and try to raise it, you need to make the denominator smaller. So to make the denominator smaller, I would subtract as well. All right. So you look at each one independently of the other. Okay, just assume the other one is at rest, see what that motion does. Assume this one's at rest, see what that motion does, and you use that to determine the signs separately. Okay. Now, of course, they are going to be getting further apart, right? Because the observer is moving faster than the source. So for that reason, this final answer is going to be less than 1,000, and we'll see that right now. So it's 1,000 times 340 minus 200 is 140, and then 340 minus 100 is 240. So the observed frequency is going to be 583 hertz. So that's how that works. Okay. So I'm going to do a little demonstration right now. So I've got an app on my phone. It's the tone generator app. And you can see I've got it set to play 1,000 hertz. All right. So what I'm going to do is I'm going to stand over here. Okay, so I'm going to take the phone and I'm going to whirl it in a circle like this. All right. And so when the phone is down here, it's going to be moving towards the microphone. So it's because it's moving towards the microphone, you're going to perceive a frequency higher than 1,000 hertz when it's in this part of the arc. And then once I go back here and I move it away, now it's moving away from the microphone. And so you're going to hear the frequency go below 1,000 hertz. So let's see if you guys can perceive it. Okay, so I hope you could hear the Doppler effect there. Now, one thing that's interesting is, from my perspective, so the Doppler effect depends on perspective. I cannot perceive the Doppler effect, all right? So, and let's try to understand why. So I'm making the phone move in a circle, and if you look at my ear is basically at the center of that circle, okay? So the phone isn't getting any closer or any further away from my ear. So there's going to be no shift. So I hear 1,000 hertz. I could not hear the Doppler effect at all. So I have no clue if my demonstration worked, okay? And I'll ask you in the Zoom room. Now, what if I turn this way and I play the sound like this? It doesn't matter where my arm is. If my arm is right here, it's the same distance to the camera, or to the microphone, excuse me, If it's up here, it's the same distance to the microphone. If it's over here, it's the same distance to the microphone. If it's down here, it's the same distance to the microphone. So if I hold my arm like this, so if I turn sideways rather and do the Doppler effect, you guys should not hear it. Or at the very least, you should hear it much less than you did when I went like this. Okay? So I'll try both. So I'm going to try and do this. You should hear very little Doppler effect. And then I'll turn and I'll do this again, and you should hear a lot more Doppler effect. So let's try it. So, all right. I hope that worked. That is my lesson for today.